So there you go. And hopefully, okay. Why don't we get on start? So last time we went through a lot of just integrals, right? All of these. There should be it's like a hour long video last time. So okay. Um yeah. Why don't we start? So application of integrals, yada yada yada. We've got right area under the curve. That should be we should know that from methods, right? So yeah, we can do this also if it was a function of y, right? So instead of, I guess, f of x, we can do f of y. And so what that basically kind of looks like, I've got an example that I'm just going to quickly sketch. What that kind of looks like is, let's say I define this as f of y. And if I were to find the area on the curve, it would be here, right? It would just be enclosed by the y-axis. So, why don't we start with exercise 2.01, right? So we have got so we've got this function, right? Sketch f of x and y. That was a bad time because they're the same function, right? So we can sketch that pretty easily. It's just gonna um negative e to the 2x. So that would be flipped, right? That would be looking uh on the y-axis or the x-axis. Is it reflected on the y or the x? Does anyone want to have a go? Flipped graph with translation. Yeah, there's the vertical translation, but how? How are we flipping it? It's just you can talk if you want. But it kind of looks like this, right? That's what it is, right? So, and obviously its intercept is at 3. So there we go. Okay, so we're gonna find the area between the x-axis and also the y-axis, and that happens to be the same, right? So we can do either one. This one's pretty easy. You can just do it. I think it's like this is just methods. So um area is gonna be equal to integral, right? Um uh, integral of 3 minus e to the 2x, okay? But we need our terminals, right? So, oh, they've given us the domain, so 0 to 4, okay? And this is just yeah, I'm sure everybody can do this. So minus 1, 2x, right? X equals 0, x equals 4. Um, yeah, and then you just sub it in. So it's going to be 12, 12 minus 1 half e to the 4. Oh, no, e to the 8 minus that's going to be 0 and that's going to be 1. So 0 minus 1, right? So let me just, sorry. And then we can easily just say 13 minus 1 e to the 8, something like that. So, yeah. Okay, cool. So that's basically that. That was just a warm up from methods. Okay, so we know that there's area between two functions, right? Um, and so you got case one where you just, it's easily top top function minus bottom, right? But when you have this, you kind of need to break it into bits, right? Because it alternates between which one's the top function, and you just break it into partitions, right? Just partition it. Um, and then um, that brings us to exercise 2.02, right? Find the area between the semicircle centered at 0, 0 of r equals with the radius equals 4 on the positive y-axis and the line y equals 2x. Okay. So a semicircle at the origin, what's the function for that? Does anybody know? No one? No one wants to have a go? Okay, why don't we do it? So basically, a semicircle at the upper half is just going to be y equals square root 16 minus x squared, right? Yeah, yeah. And then so you got also the line y equals 2x, right? So this kinda, if I were to sketch this kind of looks like this, basically. Um, right, you got radius 4, so 4, negative 4. And then you got y equals 2x, so something like this, right? So we want to find the area between that, yeah? So all of this, basically, yeah? So is there anything else? No, that's pretty chill. So we're just gonna, at the intersection, so we're first gonna find the intersection. It's just gonna be square root 16 minus x squared equals 2x. And then this is gonna be 16.
Yo, how do we know if the area is the bigger side and not the smaller right side? The bigger left side and not the smaller right side. How do
Oh,
we
so
how do we differentiate between that?
so you're saying why can't it be this side?
Yeah.
Um, because then it's not bounded between the two functions, right? It's got to be like in between the two functions. Does that make sense? This is not in between, right? This is only like through here. Um, like that's like basically the semicircle, on this half, but it's not bounded by this y equals 2x, if that makes sense.
Okay, yeah.
Yeah.
But in the left side the semicircle ends at -4. It doesn't join to the line down below. Is that still
Yeah.
bounded?
Yeah, so what we would do is basically this sort of yeah, this area, right? And then you get this area kind of, I guess, individually sort of thing. So basically it's already set up as it is. Um, which we'll do, if that makes sense, right? So because this is bounded, because remember the when it's in the negative, the sort of where it's bounded is towards the x-axis. Yeah, that's what we do area under the curves. Right,
No, yeah.
we're not gonna do that way, right? Because that's just gonna be infinite, right? So there you go. Okay, so back to the intersection. So you get this, and it's just a bit of algebra. So you get what is this? So 16, oh, sorry, 16 minus x squared equals 4x squared, right? So that's going to become 5x squared equals 16. X is going to be 6, 4 on root 5. Yeah, agree? Okay, so, okay. Then we know that y equals 2 on 4 on 5. So your intersection is at 8 on root 5. Okay, I'm just going to add a thing. I did not give enough space for that. All right, cool. Now we've got our terminals, right? Oh, actually, I should have been more specific. I reckon we don't do that one. But I should have mentioned it in the question. I think we should only be doing the oh, positive y-axis. Sorry. I even did the wrong. Yeah. Sorry guys. Don't do the left side, but if it didn't say positive y-axis, um do the left side as well. But because it says bounded by positive y-axis, we're only looking at this here, right? The shaded blue. So it's just going to be from 0 to 8 divided by root 5. So our area is going to be um, 0, 8 on root 5. And so the top function is going to be our semicircle, right? So it's going to be square root 16 minus x squared minus 2x dot dx. And so we know that the square root 16 minus x squared is in the form, um, what's it called? When we integrate that, that would be arc sine, right? So we're just going to do that. And then the other integral is pretty chill, right? So I've actually given you a very hard integral because I don't think you guys know how to do this by hand. That's my bad when I was writing the question. I'm just going to give it to you because it's a bit harsh. So we're just going to get uh, it's a trig sub, you're right, but it's not in the 1 over root thing. You're gonna have to do it like the proper way, and you're not taught that. But it doesn't have to be. Yeah, trig sub isn't in the syllabus. That's why I'm not gonna like, because it's always gonna be, yeah, I know it's x equals 4 sine theta, but I'm gonna have to do the whole thing, and you're just gonna, and you guys like don't, you'll never get something like this. Yeah, that's my bad. When I wrote this question, that's too hard for you guys. But basically what you should get in the end is x on 2 square root 16 minus x squared plus 8 sine inverse x on 4 um minus x squared, right? 0 to 8 on 5, 8 on root 5. Um, yeah. And so, yeah, we get basically something really ugly. Okay. Um, I'm gonna scratch that question. That was a bad question to give you guys. It's a bit too hard than you think. Might be, but you're no, cool, but it should be X. No, not really, no. Okay, let's just move on. That was a bad question. So we've got a parameterization here, right? Um, which makes things a bit harder, especially the fact that I've given um you some bounds instead of t, right? So you're gonna have to find out the, I guess the, what's it called, right, where it goes from. So when you prioritize an ellipse, right? So on the cos scale, you should be able to recognize that's going to be your radius on the x-axis, right? So we should be going to -2, and then it's going to be 3, -3, right? So this is your ellipse. Oh God, I can't draw an ellipse. Right? Someone like that. But we know it's parameterized from pi on 2 to negative pi on 2 to pi on 2, right? So we know that this is 0. Pi on 2 is here, yeah? Pi on 2 is this part because as you go, sorry, not that's not pi on 2. Pi on 2 is here, right? Um, no, I'm bloody tweaking. That's my bad. Pi on 2 is on the y-axis here. And you got -3 pi on 2. So that's from here. Yeah, do we agree? So basically, I'm looking at sort of this side, right? Because that's what it's parameterized. So yeah, um, we're gonna have to do a um. This is too hard for you guys as well. I don't think you guys can do this. Yeah, because you won't get a function. You won't get a function. You got to do a parametric um integral, and you guys haven't learned that. Yeah, that's too hard because you won't get this. Yeah, no, let's just skip it. Who cares? Okay, volume solids revolution. Here's the proof here. So we're just gonna skip that. Because you guys should know how to do this by now, right? So we get this first one. So we've got a region y equals arc sine x, well, where y equals 0, right? So the x-axis, yeah, and from x equals 0 to 1. And it's rotated about the y-axis. So we need to get a function of x equals, right? Y, right? So first of all, we want to do x equals sine y. Right, that's the function that we're just gonna um so basically we get what's it called? I'm gonna sketch it for you guys. So arcsine. Does anybody know how to sketch arcsine? It's like um sine on the y-axis. No, it's like you gotta reflect it on y equals x-axis. So yeah, um that's basically what it is. So it kind of looks like this, right? And so it's gonna go from 0 to 1, right? And so we're just rotating this across the x-axis and we're only doing this positive. So we're just basically rotating this part. Yeah. So, we want to find the equivalent terminals on y. Yeah. So what would those be to set up our volume of revolution sort of thing? Pi times integral function squared. Yeah, but what are the terminals? Because we know our setup for this is integral AB pi. Sorry. Oh, that's my bad. Mm. Pi Fy, this function squared, dot dy. Yeah, but what are these? What is A and B going to be? 0 to 2 pi? Yeah, yep. So that's basically it. So we get 0 to 2, sorry, pi on 2, not 2 pi. And then we're just gonna take sine 1 squared dot dy. Okay. So yes, we're just gonna do this. And basically, you're gonna have to use a trig, right? Trig identity. So, because it's even, what do we want to use? Let me get the formula book out. A double angle identity, right? Um, so basically it should be, yes. So we can see that on your formula book, it should say sine 2a equals 1 minus 2 sine squared a. All right. And so we're just gonna rearrange
I'm
for
pretty
that.
sure that's cos, isn't it? Cos 2a.
Shit, cos, yes, I'm blind. My bad. Cos 2a, yep. And then we're just gonna rearrange for sine. Yeah. So it's gonna be sine a. So sorry. Sine squared a. Whoa. Um equals cos 2a minus 1 over negative 2. Right? So we're just gonna substitute that into our formula. 2y. Okay. And it's just basically just uh integrating this. And basically if you know your methods, you can do this, right? So I think the final answer is like pi squared over 4, right? Units. Okay. Um so yeah, have a go at this. It's pretty chill. Okay. Exercise 2.05. It's another parametric thing, but we can actually turn it into a function first, right? It's going to be a lot easier, and we've got it here. So, um, do I want to give you time? So, how do we parameterize this? Or I get a function of y equals x. Anyone? Tan equals square root 1 over 1 minus x over x. I don't think that's a thing. Oh, yes, yes. So you're gonna have to use some trig identities to make it that, right? So on your formula book, let me get it back up. What do we have that's like tan and has like cos in it? Yes, we do. So what do we recognize? We can see that, okay, let's just manipulate y for a second. So y equals 2 root 3 tan, um, tan theta, right? Um, how can we express, yes, we're using sec, right? Equals, what's it? Sec squared minus 1, right? So we know that x is equal to, now we just want to put x into the form of sec, right? So x is going to be 2 cos squared theta. We want to make it sec. So it's going to be sec squared. That's about C. Sec squared theta equals 2 on x, right? So we're just going to get that into y. So y equals 2 root 3. 2 on x minus 1. Oh my God. Yes, we're supposed to. I forgot the square root. Well, what I can do is I can. Yeah, okay, yeah. Um, we're actually gonna make it a bit easier. I did forget the square root. You're right. I can't do that immediately. I'm gonna square it on the y first. So that's gonna be 4 times 3, which is gonna be 12. 10 squared theta. Okay, now I can do it. All right, so this is gonna be 12 sec squared minus 1. Right? And then now we're going to substitute. So we're going to get y squared equals, let's get rid of this. Sorry, it's either 5 o'clock. No. No, can you go for a sec? Sorry, my bad. Um, yeah. 12 sec squared 2 over x minus 1. Right? And so we can take the, yeah, I think that should be it. And then obviously
Wouldn't it be better to solve for
y.
x
Solve for
y in
x. Oh
terms of
yeah, yeah.
x?
We can do that.
Because it's
We can just rearrange, right? So we
yeah.
should getting, we can do this rearrange. Shouldn't be too bad. Y squared. What do we want to do first? Divide by 12, right? And then plus 1, and then what? Divide by 2 by whole thing. So it's going to be 24. This is going to be 2, 1.5, right? And that's going to be 1 over x. So now we just have to flip everything, and you're gonna get x equals 24 over y squared plus 12. Right? Okay, cool. So we've got a function in terms of y. Yeah. Now we're just gonna go from 1 to 3. Yeah, as given in the thing. So we can just set up our formula, right? So we know that v is equal to pi 1 on 3 x squared dot dy. Pi equals 1 on 3 24 over y squared plus 12 squared dot dy, right? And then so we get v equals 576 pi integral 1 over 3 1 over y squared plus 12 squared dot dy. Okay, so Um,
Sorry, shouldn't it be y squared plus 144? Uh, that's what I got. I don't know if I'm right or I'm wrong or
y squared plus 144. Uh, is it?
wait.
I don't think so.
No, it's not. I'm wrong.
Yeah, can someone just look back
No,
and double
no, my
check?
bad, my bad, my bad.
No, yeah,
No,
you're
you're all
fine.
good. All good.
My bad, my bad.
So, okay. How do we integrate this? How do we integrate something with, I guess, squared like that? I swear I've given you like another hard integral, and it's just like not possible for you guys to do. Uh, I think this is another hard one. Should be doable. Yeah, it's tan inverse. But I think you're gonna have to do a trig sub at this point, and you guys haven't learned a trig sub. Yeah, you're gonna have to do a trig sub. So, um, just do it on your calculator. Trig sub is not hard to explain, but it's not like you guys don't need to know it. So, I don't know, like there's kind of no point because all the inverse trigs that they're gonna give you is from your formula book. That's all you need, right? So yeah, um, no, and Trixie takes a long time. It's just like if you can just use the formula sheet, just use the formula sheet. So yeah, if you put it in a calculator, you should get something like whatever the answer that I've given you. But yeah, this is another hard question. Okay, that's basically volumes of solids of revolutions. Right? Um, it's pretty chill. You just like find the function, find the terminals, and then apply the formula. Um, what's it called? Simpson's rule. Um, yeah, it's just a numerical approach, right? We know there's trapezoidal rule as well. What Simpson's rule does is that for each strip, it's gonna like make a quadratic, right? It's gonna make a function. So it's a lot more accurate than trapezoidal because we know trapezoidal kind of just like does lines, right? Sort of thing. Um, so yeah. This is a formula, and obviously you got your um odds and your even, right? These are your even things. So if we wanted to do this, right, exercise 2.06, right, four strips to determine cos x squared, right? Obviously you can't integrate that with normal stuff, right? You guys just haven't learned that, but that's okay. So we're just gonna use Simpson's rule to approximate it. So first of all, we want to find W, right? And W is given by B minus A over N. So B and A are your terminals, right, that you're going to. And N is the number of strips that you're going to do, right? So W is going to be equal to B minus A over N, which is pi on 2 minus 0 over 4. So you get pi on 8. Okay. Okay, now it's time to get all of our f of x's, right? So I like to do you should like make a table. It makes a lot easier. So xn and f of xn, n equals 0, n equals 1, n equals 2, n equals 3, and n equals 4, right? So okay, well, n equals 0 is just when we sub in 0 to our um actually first we want to find out x of n's. All right. So because it's divided by pi on 8 for each one, right? And we're just going to start from 0 and we're just going to go up by pi on 8 for each one, right? So it's going to be pi on 8, pi on 4, 3 pi on 8, and pi on 2, right? So we've got 4 strips that goes to our terminals, which is 0 to pi on 2. Okay, and then we just sub this in to find what's it called? What we want. So we're gonna get cos 0 is just gonna be 1. Yeah. And then for the rest of them, I think you need a calculator for this. So um would someone like to do this in the calculator? Because I cannot do this in my head. So pi squared on 64 cos pi squared on 16 cos 9 pi squared on 64 and cos pi squared on 4. Okay. And once you get these values, you can just sub it in to our equation, right? So we know that the integral from 0 to pi on 2 cos x squared dot dx is gonna to um it's gonna approximate to w over 3. So it's gonna be pi on 24. Um x0 is just gonna be 1 plus, and then 4 of your odds. So these are your odd um f of x's. So we're gonna do 4 cos pi squared over 64 plus cos 9 pi squared over 64, right? Um, brackets, right? And then you're going to be your two evens, and that's going to be for n equals 2 and n equals 4. Yeah. So um, yeah. So we're just going to do that. So cos pi squared over 16 plus cos pi squared over 4. Right? Yeah, and then you just plug in your calculator and you should get some answer close to, I guess. Right? That's basically Simpson's rule. I don't think they can ask any really hard questions on this. It's just literally just stock standard approximation or whatever. Okay, cool. And then finally we have exponential PDFs, right? So this is what it is, right? Um, it's non-negative, and we know that the entire bounds is like going to be 1, right? Because you can't have a probability more than 100%. Yeah. So yeah, it's like we use it to time like waiting time for stuff. So yeah. But how do we find the average wait time? So here's a proof. Um, stock standard proof because we know that the mean is 1 over lambda, yeah? But how do we kind of get there? So does anyone want to have a go? Integrate to infinity. Okay, what are your bounds though? Yeah, yeah, you're literally just using, yes, so 0 to infinity, right? And so we're gonna do t, right? T lambda e to the negative lambda t dot dt. Yep. So then you're gonna do a integration by parts, right? So that's how we're gonna prove this. Yeah, does everybody agree? So we're just gonna do that. So we're gonna let u equals um what are we letting u? T? So du is going to be 1, right? dv is going to be e to the negative t, right? V is going to be 1 over negative lambda e to the negative lambda t. Right? We know that integration by parts is given by udv uv minus v du, right? So we're just going to substitute what we have here. T negative e to the negative t minus 1 over negative e 0 to infinity dot dt. Okay? So we're just going to integrate this. Oh, I forgot to put the bounds here. 0 to infinity. Why don't we integrate and then we'll put the bounds afterwards, right? That seems a bit easier. So let's just do the integral here. So we're gonna get minus, so that's gonna be plus, right? Plus, let's factorize the 1 over lambda out. So we're gonna get 1 over lambda e to the negative dot dt, right? So let's just do the integral now. So it's just gonna be t equals negative lambda, right? And then we're gonna get, it's gonna be negative 1 over lambda squared, right? E to the negative t dot dt. Oh, sorry, not dot dt. I'm not integrating anymore. Yep. Okay, cool. And then now we add our bounds. So t equals 0, t equals infinity. Yeah. So we're gonna do our upper bound first, which is infinity, and you can't really sub in infinity, but you can just, what's it called? Take the limit, right? Just see how the function does, where it approaches and whatnot, right? So yeah, that's what we're gonna do. So we should get that in the end. Good. So e to the negative infinity is going to be really small number. That's going to be 0, right? If we sub in infinity here, e to the negative infinity is going to be like a really, like a 0, right? So it's just going to be 0, right? That's our first time. Same with this one. Same with this one here, right? Um, so this one here, we're going to have 0, right? Minus. Now we're going to sub in our 0. So 0 here is going to be 0, right? 0 here is going to be minus 1 over lambda squared, right? And so 1 on lambda squared is what we get. But we know that e of x is equal to lambda times 1 on lambda squared, right? Which is 1 on lambda. Okay. So that's basically the proof for that. Yeah. Cool. That's it. Okay, and then the last question for tonight. Yeah, I did take the lambda out. I should have mentioned. Okay, so the last question is just the application. So we know that x be the amount the time for a customer to wait for coffee, and so you got an exponential distribution with the average wait time of 4. So e of x is 4. So lambda is going to be 1 over 4, right? Okay, so why don't we try and do this? So we can do the so a PDF. So what's the probability that the wait time is between 4 and 6.5 minutes? Right? So is going to do the integral between 4 and 6.5. Yeah. And we're just going to apply our PDF. Yeah. Okay. So that's literally 1. Put it in your calculator and you get some definite integral, right? I can get the solutions. Hold up. Oops. What are the solutions? Anyways, while we wait, we can do 2. So determine the probability that the wait time is between 4 and 6.5 minutes, given that the customer has already been waited 4 minutes, right? So what does that mean? That's like P of 4, 6.5, given. Right? That's how you would write it, I guess, mathematically, right? Given that you've already waited 4 minutes. Yeah, that's more than 4 or equal to, right? So how do we do given stuff for PDFs or just probabilities in general? So we're going to just do the probability that X is between that. Over the probability that X is greater than 4. Yeah, exactly. So we got the answer from before. So it's just going to be integral 4.6 1 over e to the 1.4 1 over 4t. And it's just going to be integral from 4 to infinity 1 over 4 e to the 1 over 4. Right? Yeah. And then basically whatever this is as an answer. Right? Cool. 3. 30% of coffees may take a maximum wait time of. So I've given you the percentage, right? So now you just have to work out, I guess, what the time is, right? Negative power. Yes, yes, I've dropped it. I've dropped it. That's my bad. Okay, cool. So how do we work out this? So we know that P r of x less than t gives us 0.3, right? So how are we going to do this? We want to make it cumulative distribution function, CDF, right? So we're going to do
Wait, can you share the question quickly again?
Yep. This is it here.
Yeah, thanks. All good.
All good. Okay, so we're going to make a CDF, and how do we do that? We just integrate, right? So we're going to go, we should be adding a dummy variable, but I'm not going to do that. It's just going to keep it as t. It's okay. So 1 over 4 e to the negative lambda t dot dt equals 0.3. Right? So we're just going to integrate this. 1 over 4. So we're going to get negative 1 over 16 e to the negative 1 over 4t t equals 0, t equals t equals 0.3, right? And then so we can literally just sub it in, right? So 1 over 16 e to the yep, minus minus. When we sub in 0 for our lower terminal, right, this just becomes 1. This here becomes 1, yeah? So it's just going to be minus 1 over 16, right? Equals 0.3. So you get plus 1 over 16. Yeah. And now you just rearrange, basically. So 0.3 minus 1 over 16 divided by negative 1 on 16 equals e to the, right? So whoever has a calculator, that would be nice. Yeah. But yeah, you just solve for t, right? And it's just a bit of simple algebra.
Oh wait, for that question,
Yeah.
can we use solve n instead of having to do all that?
Solve n. Yeah, you can. Like, I'm just showing you, I guess, the steps. And I think, honestly, I think I might, less than t. Yeah, no, I'm fine. Yeah, you can just use solver as well. So a lot of the, like, what I expect with the exponential PDFs and whatnot, they're gonna be like tech active, right? I don't expect them to be tech free unless I give you like some proof question like that one, but it's not, I don't think that's gonna happen either. So, yeah. Or this is just gonna be a simple multi-choice in the tech active, right? So yeah, there's really nothing much to it. It's the same thing. Like, if you know your methods, PDFs, you should be fine for this, right? There's nothing, it's just literally just the formula and just apply it. That's it. Okay. Cool. So we've basically finished applications, right? I know it was pretty quick. There was some questions that were like too hard for you guys to actually solve. Um, so yeah. Um, I can put the solutions for those properly later. And I can send it and I can show you how the trick sub works. Um, but like, yeah, nah, it should be all good. So yeah, I don't know. Next time, are there any questions? Probably not. It's pretty chill. I hope at this point you guys like know your applications, right? Or else it's like we're in a dire situation. Um, I'm not sorry for not being as energetic as I usually am because um um yeah. I think yeah, I really wanted to get onto I think related rates and some D's because there's some I've written some pretty chill questions that might be useful. Um and then to do modeling motion, I'm thinking of maybe just like instead of like going through everything because there's so much in modeling motion because it's just like a lot of physics, right? A lot of mechanics, sort of applied questions. I'm just gonna pick a few like hard ones and we'll work through them. Um, but yeah, that's basically the plan. But integrals should be chill for you guys. Okay. I'm gonna stop the recording now.